Hello, this is the virtual version of the lecture I gave at the APS Global Physics Summit here in Anaheim, California. My name is Nathan Pacey, and I'm in Professor Bradley Hauer's group at the University of Waterloo and the Institute for Quantum Computing. Today I'm going to be talking about how to generate pair coherent states using optomechanical systems. So as many of you know, quantum computing comes with some challenges. Quantum states are fragile and they can be easily influenced by their environment, causing decoherence over time. This means that it's difficult to scale to many logical qubits for quantum computing systems, of which error correcting codes try to mitigate this problem, but they can often be complex and resource intensive. So this sets the stage for our motivations behind the usage of mechanical systems, specifically our optomechanical systems. And some of the benefits include noise-biased error correction, the ability to exhibit longer lifetimes for different qubits, and because of the fact that they're mechanical, they have minimal crosstalks between different qubits and modes. So let's understand the math behind a single mechanical mode optomechanical system. And we're going to use the master equation and Hamiltonian to describe this, starting with our cavity mode. We then take a mechanical mode, and if we allow them to interact through this coupling term G, we're going to add that term to the Hamiltonian. Since we have a real system, the mechanical mode is going to have its subsequent mechanical bath representing the environment, of which the mechanical mode can either lose phonons to the environment or gain phonons from the environment. And you can see this represented by the rate of gamma in the master equation and the loss of B phonons with the annihilation operator B, or the gaining of these phonons through the creation operator. Then the cavity mode can also lose photons to its environment by the rate of kappa. And this is what realizes our single mechanical mode optomechanical system. So this system's useful because it allows us to realize highly quantum states like cat states. And cat states are a superposition, a macroscopic superposition of coherent states. And they evolved from a ground state via a two quanta, in the optomechanical case, a two photon process. We can see this two photon process in our master equation in Hamiltonian through these A squared terms, or these creation squared and annihilation squared terms, where the size of our cat state is represented by this alpha variable. Now, cat states come in two different types. There's even and odd cat states depending on the plus or minus between the coherent states. Here we show the evolution of the even cat state starting in its ground state. We can see the probability of the cat state move along into the even Fock states. We can see that distribution of probability as the cat state evolves from the ground state into our even Fock states. Now, to realize this cat state with our single mechanical mode optomechanical system, we simply take our pumping frequency read to tune by exactly two mechanical frequencies from our resonant cavity frequency. And we take our detuning frequency at near or exactly at our cavity frequency. And that allows us to realize this cat state optomechanically. So another reason why cat states are useful is because they can realize cat codes, which are made up of the cat code words that are used in error correcting codes. Now, to understand the cat code, we can see this block sphere representation, of which we have the odd and even cat states along the x-axis, the superposition of them along the y-axis, and the different coherent states left and right on our z-axis, which allows a mapping from these cat states to any quantum state along the block sphere, or in general in that case. And this helps us mitigate the different errors faced by quantum computing, mainly the bit flip error and the phase flipping error, of which you can see the rate related to these errors is related to the size of the cat state, this alpha squared term, of which if we take alpha squared to be much greater than 1, we exponentially decrease our bit flipping error rate while only linearly increasing our phase flipping error rate, which can be highly useful to different quantum circuits and quantum algorithms that might have these errors. So while this is good, we might be able to do something better using what's called pair coherent states, which are robust to single photon loss, meaning they can detect and correct a broader range of errors than single cat codes, which can enhance fault tolerance and increase stability and performance for different quantum computing applications and communications. So a pair coherent state is still a two quanta process like our cat states, except we now have these different quanta separated into two modes, here represented by A and B, where we can see that the difference in quanta is represented by delta, where the size of our pair coherent state is represented by gamma. So we can see this two quanta process now in these two different modes play out in our master equation in Hamiltonian for a pair coherent state. Whereas in the cat state, we had these A square terms. For the pair coherent state, we now have these terms related to A times B. And these pair coherent states have been shown to be experimentally realized in superconducting circuits by the Chen Wang lab at the University of Massachusetts Amherst, which I've been told is now moving to the University of Toronto. And they were able to realize pair coherent states using what's called a 3D superconducting cavity, and they were able to do so with this fidelity shown. So how do we do this optomechanically? Well, let's build up our single mechanical mode. And now because we have two separate modes, we're going to take a second mechanical mode along with its coupling rate and its rate of loss and gain to its mechanical bath. And then because we have the cavity, we're going to want to include the pumping and driving terms in our Hamiltonian. And this is the full system of equations for the master equation in Hamiltonian that allows us to realize this pair coherent state optomechanically. So the rate we would use, we would take our pumping frequency, read to tune now, by exactly our mechanical frequency B plus our mechanical frequency C away from our resonant cavity frequency A. Now, in the full model, it wasn't really clear where that pair coherent state equation was, mainly the terms of the master equation in Hamiltonian that lead to an ideal pair coherent state. So something that I've worked on is adiabatically eliminating the need for the cavity mode in our master equation in Hamiltonian in order to better understand how we can generate the pair coherent state. And while it may look like a complex system of equations, what you can see in these four terms is that the pair coherent state is actually built in. So when the other terms are much smaller than these four terms, we actually realize the ideal or near ideal pair coherent state. And this helps us understand what parameters we should use in order to generate the pair coherent state. So what values we should use given these parameter constraints. So that's all good. We've built up this system of equations, but we're talking about experimental physics. So we want to understand how we can actually experimentally realize this. So what we might use is something called a vacuum gap capacitor, of which come in two different types. We can either separate our mechanical modes onto two different mechanical resonators, which share a coupling to the cavity, but this sharing of coupling might cause parasitic coupling. So what we might choose to do is use the second type, which is putting two mechanical modes on a single resonator and using these modes shown at the bottom right. Now, the frequency is then constrained by the given geometry. So in the separated mechanical resonators, we could tune these frequencies individually, but now that we have two mechanical modes on a single resonator, we're subject to tuning them to the given geometry, whether that's circular, square, or some oval shape. It all comes with a different mode ratio. So if we choose a circular membrane mode, we're subject to the ratio from mechanical mode B to C of 2.3. So now that we understand how we would experimentally realize it, the different equations we're using in order to simulate it, we want to make sure that we optimize for our fidelity to achieve the best pair coherent state in simulation. So we start with a large enough Hilbert space and some size of our pair coherent state we want to achieve. And then we want to choose the different parameters we input, mainly the frequency of our mechanical modes B and C with that rate, with that mode ratio shared between them. Then we want to describe the loss of photons from our cavity, kappa, and then the coupling strength, GB and GC. So when we sweep through these parameters, we did over 1,500 trials using Bayesian optimization in order to understand the best states for optimizing our original fidelity. We found that these histograms occurred. So these histograms show the highest counts for different frequencies for each of our parameters. And you can see that they're somewhat Gaussian, which means that there's more high fidelity states in our top 200 fidelities occurring at certain rates. So we chose a set of parameters that achieved a maximum fidelity within these peak histograms. And that led us to a maximum fidelity adiabatically of about 99% and a maximum fidelity in our original model of about 96%. And in order to visualize and understand the quantumness and evolution of the pair coherent state in our system, we want to use the Wigner function and Wigner plots. But because we now have a two-mode system, a two separate mode system, we need to use something called the joint Wigner function, of which the ideal pair coherent state for a delta equals 0 looks like this hot dog shape on the bottom right. So we expect to see something like that when we go through our simulation. And that's exactly what we did see. So this is the delta equals 0 evolution of our system, starting from the ground state into the near ideal pair coherent state for both our adiabatic and full model simulations before they decohere over time. And when we look at the fidelity of these states, we see that our adiabatic model evolved a bit quicker into the near ideal pair coherent state before the original model, but then they both decohere over time. And again, they both achieved pretty high fidelities of about 98% and 97%. Whereas when we look at, we can look at different deltas, so different quanta, in our B to C modes respectively, and we see the same results. They start, in this case, with the B mode in the first excited state, the C mode in the ground state, which achieves this kind of hamburger-like initial state, and then they evolve over time into the near ideal pair coherent state for the given delta, in this case delta equals 1, before decohering over time. And we see similar results in the evolution of their fidelity, where the adiabatic system evolves a bit faster into its ideal pair coherent state, and then the original does as well afterwards before they decohere over time. So in conclusion, I've shown some of the potential for optomechanical systems to generate CAT codes, showing that they can have longer coherence time with minimal crosstalk, which can help to reduce the number of errors for quantum circuits, which could lead to larger logical qubit systems. I've then shown how we can generate pair coherent states and help improve some of these even more, achieving simulated fidelities of about 99% adiabatically and 96% in our full model, which leads some things we could work on for the future, including refining our parameter space to be used in experimentation, so to be used with these vacuum gap capacitors, with the potential to expand these ideas, these simulations and systems and models onto different systems like photonic crystal nanobeams and superconducting circuits. So thank you very much. I hope you enjoyed my talk. I hope you learned something about pair coherent states and optomechanical systems. And I'd like to take a quick second to thank my team from the University of Waterloo and the Institute for Quantum Computing, especially Professor Bradley Hauer. And we're looking for postdocs and students who are highly motivated to work on this optomechanics and superconducting circuits work. And yeah, thank you very much.